Okay, this is my solution of the problem that we did on Monday of the first full week. And this was the moving man problem. And I really encourage you to go play with this. This is called a FET, which is a, a set of animations and experiments that you can do of various physics ideas. And in fact, if you just Google moving man and FET, you will find it. But there's also a link on the PowerPoint presentation of these problems. Anyway, we did a problem where I showed you the output of playing around with the moving man. And there was a time and a velocity graph. And it looked like this. And the first thing I asked you to do is to describe in words what's going on here. And so one of the things I note here is that there's a positive velocity in the beginning, and then there's a zero velocity, and then there's a negative velocity. And so in order for the velocity to be first positive, then zero, then negative, what that means is that the man turns around. He starts walking in one direction, whatever the positive direction is chosen to be. And then slows down uniformly, eventually coming to a stop. He then changes direction, speeding up in the negative direction, until the end at about 12 seconds. Okay, so I'm using here that this is about 12 seconds, and from the graph, this was about 6 meters per second. So the next question asked to graph the position as a function of time. And so to do that part, if I'm just going to do a sketch, I might draw something like this. Now truly, you don't know really just from the velocity graph what the initial position is. So I can pretty much pick anything I want. But what I do know is that the position has to be increasing at the start in the positive direction. And how I know that is that the velocity up here is positive. So positive velocity means wherever I start, even if I start right here, the velocity has to be in the positive direction. I have to be increasing my distance, my position. But then I know that the velocity is getting smaller and smaller, so while I'm still going in the positive direction, the slope of the curve starts to flatten out. And then eventually the slope of the curve is zero, so it flattens out so that the slope of this curve instantaneously is zero, and then it starts heading in the other direction. So this curve is a parabola. And the kinematic equation that we're using looks like this, that x is equal to x naught plus v naught t plus 1/2 a t squared. So I don't really know in advance what the x naught is. Now we played around with this a little bit, and it turns out that I did start him at a negative 10 meters, but that's actually not really key for this problem. Let's go ahead and use it though. So this was negative 10 meters from observation. And so the position here at any later time is negative 10 meters plus the initial velocity, and the initial velocity is up here at 6 meters per second, 6 meters per second times time plus 1/2. Oh, we need the acceleration. Well, the acceleration is defined as the change of velocity over time, or the instantaneous rate of change. But for constant acceleration, these two things are actually the same because it stays the same whether you're looking at a very small interval or whether you're looking at a really big interval. So in fact, it goes from 6 meters per second down to negative 6 meters per second. And so the final is minus 6, and the initial was positive 6 over 12 seconds. And when I add these together, I get minus 1 meters per second squared. And I'm feeling good about the negative sign because it is indeed acceleration in the negative direction. So this is 1/2 minus 1 t squared. And you can simplify this as much as you want, but this is the answer.